And I say with low common support here, that's kind of a common problem with propensity score matching, so I'm interested in it, but I look at a couple other practical problems that come up with propensity score matching and how GME might address them. So it's fairly popular methodology, but just a quick summary. Propensity score matching is an evaluation strategy that's commonly used, and people like it because it's very easy to implement. All you need is some treatment group you're interested in, a control group, and they have to have the same variables on a lot of covariates that presumably selection occurs on. And when you have that, you can implement PSM. Whether it's a good propensity score match or not is a different question, but it's common for that reason. So you start with the discrete choice model, where you're predicting the probability of treatment status on these covariates, and then you use that predicted probability in some kind of second stage to reweight the control group to make them appear like the treatment group, so it mimics random assignment in that sense. The second stage could be a model itself. You could have regression adjustment, or you could, of course, just compare means once you've got samples that are balanced on the covariates. Common problems, though, with propensity score matching are low common support. So your treatment group and your control group are so different from each other. There's only a small amount of cases that have common values for the covariates. So even when you reweight the control group, you don't have sufficient sample size to get a precise estimation. And then selection on unobservables. If the selection process is determined by something other than the covariates you have, simply matching on covariates isn't going to get you an unbiased estimate. So I look at the first one today. The second one I'm going to hope to get into in the future. And so the goal of this paper is to use GME methods specifically for that first stage of predicting the probability of treatment. So the only thing in the literature that really gets close to this is a paper by Hain-Mueller in political analysis, I think. And it's an information theoretic approach to PSM in the sense that he's maximizing entropy, and he motivates the information theoretic estimators in the same way that we're used to. But it's what's called a balancing approach rather than a full GME approach. And the difference is that he's maximizing the entropy for the control group, but on the left-hand side, he just has the moments of the covariates of interest of the treatment group. So he takes the mean of the covariate, and then he reweights the control group using maximum entropy to provide weights that match that, that moment. So to get a sense of what he does and how it's different from what Paul just presented, the H is the standard entropy measure, so he's minimizing the non-negative rather than maximizing the negative. On the left-hand side are these treatment group moment constraints. And then he has the proper probability weights that Paul discussed. So it's a little different. It doesn't go quite as far as the generalized approach where we actually are estimating a discrete choice model of treatment status. So this should look familiar because Paul just discussed it. I'll go over it quickly. Of course, we're maximizing entropy. We have both the entropy of the P's for the covariates and the W's, which are the weights on the error terms, because the error terms enter the entropy objective as well. And then it's subject to the model itself. Treatment as a function of the P's and the weights. And then the proper probability constraint in this case, of course, is just P plus 1 minus P equals 1. And Golan, Judge, and Perloff is the site that Paul mentioned, and then also Atkins looks specifically at binary choice models. And it's kind of a more, it's an easier discussion than Golan, so it's a nice place to start. And Golan looks at multinomial choice. So that's all what we saw in the last presentation. So then with propensity score matching, of course, I want to take probability of treatment out of this. And so it's just the expected probability of treatment from that model. That's fairly straightforward. The predicted probability of treatment is the sum of the individualized predicted P's and the E weights. So E is just the support, the B's times the W's that Paul showed you. And then once you have this propensity score, all sorts of matching and weighting strategies are possible. So I'm just exploring this, so I use kernel weighting, but there are 5 or 6 others that are commonly used. And then you can do with regression, adjustment, or without, and I'm just doing comparison of means in this case, but these are all. Okay, so basically what I do is I run Monte Carlo simulations, 1,000 repetitions of the model that I'm going to show you. Treatment is determined by a logit function of, I just generated 5 different x variables, and I have these beta coefficients that I made up, and if the logit function is greater than 0.5, I assign it to treatment. If it's less than 0.5, I try and assign it to the control group, and of course the error term, the standard deviation of the error term determines how much common support, how much overlap there is between these two groups. Obviously, if the error term were 0, then we wouldn't have any common support to work off of. A covariance structure is imposed as well, but it's not shown here. And so then what we're actually interested in estimating comes in the second stage. So I have my y outcome variable that's also a function of all of those covariates from the first stage. And then, of course, it's a function of the treatment, because what we're interested in is the treatment effect. So I just choose coefficients for all the covariates, but then what we're interested in estimating is this gamma coefficient on the treatment, which I've just assigned to 1.75. So I have the actual value. So this is the treatment effect that I'm looking for. And I have the actual value of the treatment effect in the graphs I'll show you later. But that's the number to keep in mind. So I simulated with 1,000 repetitions. I do a couple variations that I'll show you. First, I vary the sample size. Obviously, with large sample size, we're not as worried, but I take that down to 100, which is very small for running these things. But if you're evaluating job training programs or something like that, where sometimes you're dealing with small sample sizes, these are the practical obstacles that people run into. So if GME can outperform at these small sample size, that's important to know, I think. And then the standard deviation on the errors, I start real large at 5, so there's a ton of common support, and I incrementally work that down to 1, so there's less common support. And that's another practical problem, is low common support in these tests. And then Paul alluded to the fact that if you have non-normal error distributions, that's another area where GME seems to outperform standard models. So I start with the normal error distributions, and then I look at log normal to see if GME does any better. So the average treatment effect on the treated is usually what's of primary interest in these studies, and that's what I present here. But I also produce just the average treatment effect, and they all follow exactly the same patterns as the ATTs, so it's basically the same results. Okay, so I want to show the common support variation that I look at. This is the biggest common support. So the red line is so on the horizontal axis is the probability of treatment. The red line is the control group, and the blue line is the treatment group. And so even though there's a lot of mass on either end, you can see there's a lot of common support here. And so this is where the standard deviation of the error in the first stage is 5. So even though it's unequal, there's still a lot of sample to work with to match on in the middle. Now when I reduce that standard deviation to 1, you can see that the common support really evaporates quickly, and there's less to work with. So those are kind of the two ranges of the common support that I'm looking at. All right, so these are the results. Okay, so these graphs are kind of deceptive in 2 ways. First, notice that this doesn't go down to 0, but it was nice to use this because we're working right around the actual value of 1.75. And then also notice my sample size decreases because I'm moving from left to right, the less stringent to the more stringent. So all of these graphs I should probably change. They're a little misleading in that sense. So the actual value, so these are the mean average treatment effects, and what I'm varying here is sample size. So each data point on the graph is the mean average treatment for those 1,000 simulations that I did at that sample size. So that's 1,000, that's 1,000. And of course, the logit version and the GME version are using the same data in each case. So as you can see on mean average treatment effect on the treated, the GME is much closer to the actual value than if I just use logit in the first stage. And what was interesting is that this didn't change as much, very much in either cases. I reduced the sample size. But mean average treatment isn't just what we're interested in. We're also interested in the variability of these estimates. So I looked at the root mean square error, and this looks exactly like if you just plot the standard deviation of the average treatments. And the logit does outperform the GME on the root mean square error. So in other words, GME is more accurate on average, but it's got a lot more variability. So in any given instance that you use it, you're a little farther from the actual value than the logit is. And that is very sensitive to sample size. So that's a concern as far as practical use, right? It's nice that the mean ATT is close, but that's a real concern. So here I'm varying the standard deviation of the error in the data generating process for the treatment. So this is getting less common support as I move to the right. And again, this is the mean average treatment. And again, GME outperforms the logit. And this is very sensitive to the standard deviation. The logit gets worse over time. So that's kind of what we saw earlier, but with a little bit more change as we move along the horizontal axis. But the root mean standard error showed the same problem. GME still doesn't perform quite as well. So then the next thing, so I redid all 4 of those just with a log normal error rather than the normal error to see if that changed the performance. The mean ATTs look about the same. Again, GME does better.
Sorry, can you give an intuition for why that is the case actually? So I mean that's a bias there, right? I'm confused now because it looks a bit too good to be true. So could you say something about is that a known thing or is that?
So I'm not sure I was concerned about that as well, and I think it might have to do with. I mean, some of these, it might have to do with the common, so so let's see, for the common support, when I varied the sample size, I think I took an intermediate value of the common support. So it may be a common support issue that it's not a perfect case in the first place. And we don't expect PSM to give unbiased, if there's, I'm not sure, I might have to, that would be my suspicion that it's something going on.
So, but you mean the assumption or the standard approach is to have this common support and deviating a little bit from that assumption. Is that what you're saying?
Yeah, well, so I'm varying the common support because in the real world we're concerned about that problem. So I forgot exactly what common support I did when I varied the populator. Because I kept the common support constant, obviously, when I varied the sample size.
The degree of common support.
The degree of common support,
yeah,
right.
Okay.
And so, and I think it was like an intermediate value of this. So you already have some problems built into it, although we hold those problems constant. But yeah, again, they're both very close. Which is precisely why I didn't have the origin at 0, so I could actually show you that they're different. But yeah, it is biased, and it's consistently biased. It's not like it's jumping up and down around it. I'll probably have to check that. Do you have any thoughts on, or you're just curious yourself?
Well, it looks as if, of course, you mentioned the RFSE issue. And now you're saying, well, maybe these are within simulation error, I don't know. But in principle, I would say, I mean, I'm not an expert in this area, I'm here to learn, but if there is this actual value that you feed in down there, and the logit is up there,
yeah.
And it's always up there, it's far away,
yeah.
Then your thing is doing much better. That's the way this looks, and I was a bit surprised to see that.
Yeah. So the log normal errors is what's next, and I rerun the same 4. So we have the same pattern, although that is a puzzling aspect of the pattern. So the root mean squares, as we get to a smaller sample size, GME starts to perform a little better at that very small end, but for most of it, the logit is still performing better. The means, when I change the common support, look the same as the previous, so I'll skip over that. The only interesting difference here was when we look at the root mean square, we're varying the common support in this case. GME is performing better for most of the stretch here. So I don't have a sense exactly of what's going on here, but this does, we do know that logit really relies on a lot of these normal distribution assumptions, and so GME is a little more flexible in the distributional, because entropy is free of any of these distributional assumptions. That's why people like maximizing entropy. You don't build those specifications in the model, so it might be related to that. So these are very preliminary results. It seems to do better on the average ATT, but there are these concerns about how volatile GME-PSM. And then next, I'm just going to try all kinds of alternative matching strategies. I need to investigate some of these issues of what I've actually got here. And then it'd be nice to go to actual National Supported Work Program is kind of the standard benchmark data you can use for experimental methods again, so it'd be nice to get into that.